Namaste and a very good morning to all of you. I welcome you to my channel, The Outlier. My name is Mithun. In today's video, I'll be talking about how to build a Quest model. Quest stands for Quick, Unbiased, Efficient Statistical Tree. I repeat, it stands for Quick, Unbiased, Efficient Statistical Tree. We will be looking at the features of the Quest algorithm. Also, we will talk about the advantages and disadvantages of this algorithm. Later, we will go ahead and build a Quest model to identify the profile of bank loan defaulters. Let me spend the first couple of moments explaining the dataset that you're seeing in the screen. This dataset is called as the bank loan dataset. It is present in the samples folder of SPSS. As you can see, I have approximately 10 variables in this dataset. There are customer demographics like age of the customer, education level of the customer, the number of years that the customer has spent with the employer, the number of years that the customer has spent in the current address. The next variable that I have is income. The next variable is debt to income ratio. We have credit card debt in thousands. We have other debt, and the last variable is default. The last variable is going to be my dependent variable. As you can see here, this is a dichotomous variable. One indicates that the customer has defaulted on the payment of the loan. 0 indicates that the customer has not defaulted on the payment of the loan. Let's now proceed to look at what is the sample size in this dataset. As you can see, there are approximately 850 records in this dataset, which is a good sample size. With this background about the dataset, let's now proceed to execute a Quest model in SPSS. I am in SPSS now. As you can see, this is a blank file. This is blank because I've not loaded the dataset. Let me quickly load the bank loan dataset. I'll go to the File menu bar. Use the option Recently Used Data. SPSS displays 10 recently used files. Right at the top, the very first file is bankloan.sav. .sav is the extension of SPSS files. Let me go ahead and click on this. Yes, the file is loaded in SPSS. Now we can move to the Quest algorithm. But before moving on to the Quest algorithm, you can see the last 3 variables, that is predicted default, are of no use. So let me select these last 3 variables and remove them. How do you build a Quest model in SPSS? To build the Quest model, you need to go to Analyze menu bar, then proceed to the Classify option. The 5th item from the top is what is called as Tree. Let me go ahead and select the Tree option. This opens up a new dialog box, which is called as the Decision Tree dialog box. In the canvas to the left-hand side, you can see all the variables that are present in the dataset. To the right-hand side, there are 2 options. The first is dependent variable and the second is independent variable. I will be using the last variable previously defaulted as the dependent variable. The rest of the variables, starting from age all the way to other debt in 1000, will be used as the independent variable. You can see here the growing method. The default growing method that SPSS uses is called as the Shade algorithm. Let me click on the drop-down menu. The last option here is what is called as quest. So when you choose this option quest, SPSS runs a quest algorithm. Those of you who are very new to quest algorithm might want to know about what are the features, advantages, and disadvantages. At this moment, I'd like to take a pause and speak about the important features of quest algorithm. The very first option, the very first feature is about binary splits, which means quest performs binary splits of the data at each node. The second point is variable selection. Quest algorithm uses statistical tests to select the best variable for splitting. Third condition is robustness. Quest algorithms are designed to handle noisy data efficiently. I repeat, quest algorithm is designed to handle noisy data efficiently. The fourth option is about speed. Quest algorithm is very efficient and manages faster processing times as compared to some of the other tree algorithms like CHAID. The fifth point here is about independence of splits. Quest ensures that the selection of a split point is independent of previous splits. So these are the 5 important characteristics of the quest model. Binary splits, variable selection is based on statistical tests. It is very robust and can handle noisy data. It is very fast, and it ensures that the selection of the split point is independent of the previous split. What are the 5 important advantages of this algorithm? Accuracy. Quest generates high prediction accuracy due to optimal split selection. Second, efficiency. Quest performs faster processing and has lower computational cost. Handling noise. It effectively deals with noisy data. Number 4, reduced bias. With the quest algorithm, you can expect minimized bias in variable selection. Let me say this again. With a quest algorithm, you can expect minimized bias in variable selection. The fifth point is scalability. Quest algorithms are scalable to large datasets. With any algorithm, you have disadvantages. There are 5 important points about quest. First is complexity. To execute a quest algorithm is not so easy because it is more complex to implement a quest algorithm and understand the output of the quest algorithm as compared to simpler algorithms. Number 2, quest algorithm is limited to binary splits, which may not always be optimal. Number 3, data sensitivity. Quest algorithm is extremely sensitive to the specific characteristics of the dataset. Number 4, overfitting problem. Quest algorithm is prone to overfitting if not properly tuned. Number 5, limited use cases. It may not be suitable for all types of data or all types of business problems. So we have spoken about the features, advantages, and disadvantages of the quest algorithm. At the right-hand side top corner, you have what is called as the output option. Let me go ahead and select the output option. At the top, you can see tree, statistics, and rules. Let me select the statistics option. There is nothing that I want in this particular tab, so let me proceed to rules. If you want to generate rules, you can click on Generate Classification Rules. The syntax will be in SPSS. You can also select either SQL or simple text. I have selected the simple text option here. Let's now export the rules to a file. I'm going to call this as test double five. Let me select the location where I want to save the file. Let me give the file name as test55. I'm going to save this in desktop and click on continue. I can now proceed to the validation option. As you can see, there are different ways in which you can validate the output. The first is none. The second option is cross validation. Number of sample folds, the default option is 10. We can change this to 5. SPSS gives me a small description. It says cross validation is not available for cart and quest methods if pruning is selected, which simply means that if we have to perform 5-fold cross validation, we have to avoid pruning. You have the second option, which is split sample validation, using which you can split the data into training and test. I'll avoid this and go with the cross validation option. Let me click on continue. The third option from the top is criteria. Let me go ahead and select the criteria. You have the growth limits, minimum tree depth. If you want to control the minimum, my apologies, the maximum tree depth, you can specify a number. By default, the maximum number of levels is 3 for the shade algorithm. It is 5 for cart and quest. The minimum number of cases can be specified here. By default, under the parent node, you have 100 records. For the child node, you have 50 records. You can experiment with different options at a later stage if the first attempt does not give good results. Next, you have the quest tab. As I mentioned earlier, quest uses statistical significance level for splitting nodes. The default criteria is 0.05. You can also experiment with different numbers here, like 1% or 10%. There's a description which says an independent variable cannot be used to split a node unless its significance value is less than or equal to the level you specify. You can relax this criteria or be slightly aggressive once you see the output of the quest model. Let's now choose the option pruning. Pruning is a great way to avoid the overfitting problem. However, since I've already specified cross-validation, 5-fold cross-validation, I will be avoiding this particular option. Let me click on continue. We can go to save. We can choose the predicted value as well as predicted probabilities. Hit the continue button. With these settings, we are all ready to run the quest algorithm. Let me hit the OK button. What you're seeing is the output window of SPSS. To the left-hand side, you can see the output that is generated. You have different options like title, notes, active data set, so on and so forth. You also have model summary, which produces a table with description of what you have chosen as the dependent variable. You can see here previously defaulted. It gives you the list of independent variable. The validation criteria is cross-validation. The maximum tree depth that is used is 5. The minimum number of cases in the parent node is 100. The minimum number of cases in the child node is 50. As you can see here, SPSS also gives you the results. Debt to income ratio is identified as the best predictor, followed by credit card debt in thousands. The third important variable is other debt in thousands. The number of notes is 5. Number of terminal notes that we have obtained is 3, and the depth of the tree is 2. Let's quickly go to the tree diagram. We have got a very short tree. Let me double click on this tree. We can control the visibility by choosing 200%. So this is the output of the Quest model that we have built. Right at the top, what you're seeing is a box which represents the distribution of the dependent variable. As you can see, in my dependent variable, there are 74% non-defaulters and only 26% defaulters, which means that there is a class imbalance problem. Right below the parent node, you see debt to income ratio. So debt to income ratio is identified to be the best predictor in identifying whether a person will default on the payment of the loan or not. You can see here, adjusted p-value is 0.000 and the F statistic that is reported is 124.8. SPSS also reports the degrees of freedom for the F statistic. As I mentioned earlier, the best independent variable is identified based on statistical significance testing. How do we interpret these results? When the debt to income ratio is bigger than 18.3, I repeat, when the debt to income ratio is greater than 18, the predicted class is yes, which means approximately 60% of the defaulters you can obtain by looking at a debt to income ratio of greater than 18. Question is, what happens when the debt to income ratio is less than 18? If the debt to income ratio is less than 18, you have to look at another set of criteria. Here, this represents node 1. The majority class here is non-defaulters. The minority class of 21% is of defaulters. We can't stop here because this is not the terminal node. Let's dig further. We have to look at the second important criteria when the debt to income ratio is less than 18. When the debt to income ratio is less than 18 and the years with the current employer is greater than 7 years. Let me repeat this point. When the years with the current employer is greater than 7 years, the majority class is non-defaulters. You can see here 90% of them are non-defaulters and 9% are defaulters. What happens when the years that the customer spends is less than 7? The majority class here is again non-defaulters. We are able to capture 65% non-defaulters and 35% defaulters. So this is how a Quest algorithm works. It gives you binary splits. As you can see here, there are only 2 splits: debt to income ratio less than 18 and greater than 18. You do not get multiple splits. It's very simple and easy to understand. The criteria that it goes by is the p-value. We can experiment with different p-values if we want. I'd like to draw your attention to a couple of important points here. One is the way in which you want to display. The default orientation is from top to bottom. You can also choose the option left to right, in which case you have the dependent variable here and you have to go from left side to right side to interpret the results. You can choose the third option wherein the orientation will be from right to left. I've not seen too many people produce a decision tree which moves from right to left. When it comes to displaying the results, I'll go back to top-down approach. There are three options that you have. One is show tables in the tree node. The second option is show charts in the tree node, in which case you can see that SPSS produces bars instead of actually showing you the numbers. The third one is to show both the tables as well as the charts. The first half will report the actual numbers. Below this, you will be able to see the distribution of the bar chart. I'll go back to the original option of choosing the table in the tree node. Let me close this. With any model, there is always the problem of misclassifying an individual. Let's look at the risk of misclassifying an individual. The risk estimate that we have obtained under cross-validation is 0.23, which means there is a 23% chance of us misclassifying an individual. What does this 23% mean? It simply means that the customer may be actually a defaulter, but the Quest model may call him as a non-defaulter. Similarly, the customer may be a non-defaulter. The Quest algorithm might misclassify him as a defaulter, which is dangerous. We want the risk value to be lower. More than the risk statistic, I'd like to draw your attention to the classification table. This is also popularly called as the confusion matrix. Here you see along the row the distribution of the dependent variable. It is broken down as non-defaulters and defaulters. And along the column, you can see the predicted class, which is non-defaulters versus defaulters. The golden rule while interpreting the confusion matrix is to look at the diagonal elements from top left to right bottom. Why? This is because it represents the correct classification. So there are 480 actual non-defaulters who have been correctly identified and called as non-defaulters. They have been predicted correctly as non-defaulters. Similarly, there are 53 defaulters and the Quest model has correctly predicted them as defaulters. However, there is a big number of 130 which have been misclassified as non-defaulters. This is a cause of worry. When it comes to the percentage of accuracy, in classifying non-defaulters, 92% is the accuracy. When it comes to classifying defaulters, 29% is the accuracy of the model, which is low, and therefore we need to experiment with different hyperparameters. That is for a different video. The overall percentage of accuracy here is 76%. There's one more thing that we need to do, which is to go back to the data set and look at our original data set. This is the original data that we have. As you can see here, SPSS has generated new columns. SPSS has generated the predicted value, predicted probability 1, and predicted probability 2. Have a look at the column default, which is the actual dependent variable. The first customer belongs to class 1. The model has misclassified him as 0. This is clearly a misclassification. The second individual belongs to class 0. The model has correctly classified him as 0. This is 0. Again, the predicted class is 0, which is good. 0, and again predicted as 0. Looks like the model has done a fantastic job of identifying non-defaulters. It has done a very poor job of identifying defaulters. You can see there are two columns, predicted probability, 0.90. One question is, why And on what basis are we predicting the value for the first customer as 0? The answer is very simple. There's a 90% chance that the customer belongs to the class 0. Therefore, the model has classified the first individual as 0. There's barely a 10% chance that the first customer belongs to class 1. Therefore, since the number 90% is greater than 10%, the model has classified the first individual as 0 instead of 1. The same principle works for the rest of the cases as well. Before closing, I'd like to quickly show you the rules that we have generated for the Quest model. Remember, I had saved a file called as test55 in desktop. You can see here, this is the notepad file. The first set of rules are for node 3. You have simple if-then condition wherein it says if the debt to income ratio meets a certain criteria, what is the course of action? The prediction here is 0 and the predicted probability is 65%. Similarly, we have node 4. In node 4, the prediction is 0 and the predicted probability is 90%. Last but not the least, we have node 2, wherein the predicted class is 1 and the predicted probability is 58%. With this, I have come to the end of today's video. In today's video, we have seen what is the Quest algorithm, what are the features, advantages, and disadvantages of the Quest model. We have used the Quest model to identify the profile of bank loan defaulters. We found out that debt to income ratio and years with the current employer are the most important variables. We have learned that Quest gives us binary splits. It is based on statistical testing. It uses the p-value approach. We went on to score each and every customer. Also, we generated the rules for the dataset. I thank you very much for watching this particular video. I request you to subscribe to my channel, also like and share my videos. Thank you very much once again. Have a great day ahead.